Good morning, everyone. I've got the top of the hour, so let's go ahead and get started. Welcome to Saturday Science. I'm Brad Jolliffe. I'm the director of the McDonald Center for the Space Sciences and your host for this morning. Today's the fourth in a series of space science related lectures. And this morning, we're very pleased to have Professor Kun Wang speaking on results of some of his recent research. Before I continue the introductions, let me just remind everybody, please try to keep your microphones on mute. If you do have a question, please put it into the chat or raise your hand at the end of the presentation and we'll get to it. So to continue the introduction, Professor Wang uses isotopes to investigate the volatile element contents of all kinds of materials, Earth rocks, moon rocks, meteorites of all kinds, and even Martian rocks. He'll tell us about that. He and his students have recently published results for Martian rocks, and these results have very important implications for our knowledge of the planets of the inner solar system and how they came to have the characteristics that we observe today. The title of his lecture is Water on Mars, New Study on Martian Meteorites. Kun, it's a real pleasure and great to have you giving this morning's lecture. Why don't you go ahead and take it away?
Thanks, Brad. Thanks for the introduction. Thanks, everyone, for coming here to attend my talk. I'm really glad there's so many attendants in the Saturday Science session. Actually, I have been attending this session for at least 10 years. I was a student at WashU prior getting this position here. So back to 2009, 2010, I think that was the first time I regularly attended the Saturday Science session in physics department. It was really fun to go to listen to something very different from what I do, usually about cosmology, astronomy. So I'm very glad this is the first time I'm invited to give a talk here. For today's talk, I'm going to the topic of today's talk is water on Mars. First of all, just give you an overview of what I'm going to talk about for the next 40 minutes, 50 minutes. And I'm going to first overview some historic perspective of water on Mars. And then I'm going to move on to some modern understanding, modern knowledge, what we have learned about water on Mars. And then in the very end, I'm going to tell you a little bit of my own research, because as I just said by Brad, we have just published a paper like 2 months ago with a new suggestion, new idea, how do we understanding water on Mars. We have a slightly different conclusion compared to people in the past, so it's a little bit controversial, but there are a lot of news report on this. If you read the news from WashU, there are also other news from Time, from Newsweek, from NPR. So there are a lot of report on this like a month ago. So I'm very glad to share this with you. Of course, this my new study is very new. A lot of people will try to confirm it. So I'm still very open to discussion about this. So you're welcome to discuss with me after the talk. So first of all, when we look at our Earth from the space, the first important thing, the first noticeable thing about our own Earth is covered with ocean. In fact, our Earth is the only known planet to have liquid water on the surface. Because water is quintessential to life, so understandably, our Earth is the only habitable planet in our solar system, the only known habitable planet in the universe. In contrast, our solar system neighbor, Mars, today's Mars is very cold and dry, and we know there's no liquid water flowing on the surface of Mars. But in the past, through many, many years study of Mars, through remote sensing, through in situ study by rovers, we knew early Mars could have a very different climate. The temperature is warmer, the liquid, there are more liquid water flowing on the surface, so it's much warmer and wetter. And but how did we reach to this point? How did we started to study the water on Mars. This has to go back to more than 100 years ago. It's already 110 years ago. If you open a New York Times magazine, a New York Times Sunday magazine on August 27th, 1911, you will see this sensational news on the cover. Martians built 2 immense canals in 2 years. Vast engineering works accomplished in an incredible short time by our planet neighbors. So this news on New York Times is basically, if you look at the picture on the left, if I'm zooming in to see this picture, these 2 pictures shown you here are the surface of Mars drawing by Percival Lowell 2 years apart. The one on the left is the 2 years before, the year on the right is 2 years after. Percival Lowell is an astronomer, is a self-taught astronomer, and he, after 2 years observation of the surface of Mars, he observed there are some new canals has been built. Because of that, he is proposing, and this is even a more detailed picture, drawings by Percival Lowell. You can see there are a lot of detailed drawings on the surface of Mars. A lot of linear features has been assumed by Percival Lowell as man-made canals. So back to 110 years ago, people already start to be very interested on water on Mars, and they even found some evidence there could be some man-made canals to transport water, transport ships between different locations. And Percival Lowell even wrote 2 books on this, and the first one he published in 1906, Mars and its Canals, and later he published another because what he saw is canals, and he assumed that's man-made, and then he assumed there's some life, some kind of intelligent life living on Mars. So he wrote a book in 1910, Mars as a Abode of Life. So Percival Lowell's idea is not his original idea, or his idea mostly came from previous astronomers. For example, Giovanni Schiaparelli, which is an astronomer, an Italian astronomer. He was the first person studying Mars for a really long time. He even drew a map. This is the figure on the right showing you this Schiaparelli's 1877 map of Mars. He was the first person discovered all these linear structures on the surface of Mars. And he's Italian, so in his map, he called those linear features canali, which if you translate into English, the correct translation should be channels. So Giovanni, he didn't infer those linear features as man-made canals, but because the translation, this mistranslation from canali, channels, into English, canal, this mistranslation made later people assume those linear features could be man-made, but Giovanni himself never inferred those linear features could be man-made. He probably assumed there's some kind of natural rivers. But in fact, if you look at a picture of Mars taken by a telescope back to 100 years ago, as I shown on this left corner, you can't possibly to see the picture, to see the surface of Mars in such details. A lot of those features are mostly due to illusions or visual illusions or some kind of imaginations. So although some of the names, some of the basins, some of the names from the original 1877 map still remained, right now we call a lot of basins on Mars using the same name given by Schiaparelli, but a lot of those smaller linear features, they don't actually exist because at the time, the telescope is just not good enough to tell the difference. And I know a lot of people attending this lecture, astronomers or people interested in astronomy. This picture, the picture on the left is the 2 photos of Mars was taken by Dan Parker. He's a retired physician but after he retired, he's very interested in astronomy. So he's taking a lot of good pictures of Mars. He's using a 17-inch telescope. This picture on the left, taken by him, after imaging processing, can even match to the picture taken by Hubble on the right. Hubble Space Telescope is the best telescope we have as human beings. It's the best picture we can take from Earth. So my point here is, even current day, the best telescope, including Hubble Space Telescope or telescope, the ground telescope, such as the Parker's telescope picture taken by Parker, with the modern technology, imaging processing, overlaying all the imaging together to enhance the features, you can't possibly see the very thin rivers on Mars. So all these previous stories about rivers on Mars has no scientific foundation, because it's not possible using a telescope on Earth to see those small rivers. And this, for example, just give you example, sometimes human illusion or the visual illusion can give us a very wrong idea. And this is an image taken by Viking orbiter in 1976. This is a very famous picture showing the Martian face on Mars. So this in the middle, there's some kind of topography, because the shadow, because the sun, it looked like a human face. So since 1976, even with the modern technology, sometimes the picture give you some illusion, which make you have some wrong implications. Just to really look at this same topography again, using a 2009 Mars reconnaissance orbiter image, you see it's just a small sand dune or mountain, a hill. So it's not a Martian face at all. Okay, back to the main topic of today's lecture. We have been very interested in water on Mars, but only until 1970s we start to have the ability to really tell, to distinguish rivers on Mars. Prior than that, the technology is not enough. Telescope on Earth is not possible to distinguish the small rivers on Mars. And in 1970s, since the start of the Mars exploration, particularly those Martian orbiters, they're orbiting Mars many times, taking pictures. We first found there are actually rivers. Those pictures showing you a dendritic valley network, mostly due to previous rivers, paleo rivers. Those are evidence. Those are morphological evidence for liquid water on Mars in the past. Those rivers has dried. Now they're just dried river channels, but we assume in the past there must be rivers. And if you look at some newer pictures taken by recent Mars orbiters, much higher resolution, you see branching valley system on the left, you see incised channels and the paleo lakes on the right. So there's undoubtedly, there's so many evidence there used to be a lot of river flowing on Mars, although they're dry right now. Again, not only rivers, but also lakes. When the water flow from the river to the lakes, the current was very high. So all these sediments in the river, they were carried by those waters. But when the river reaching an open area into the lake, the current, the velocity of the water become very slow. So those sediments carried by water will deposit right at the river mouth. So you find those deltas are the sediments formed from the river carried sediments. So we did find a lot at the end of the river, when the river entered into a bigger space like a paleo lakes, you found those deltas deposit in a lot of localities. And many of you may know the picture on the right is showing you the G0 crater, where you find a very big delta. That's where the Perseverance rover landed early this year. So right now it's exploring that region because we know at that region used to be wet, used to be a lake, used to be have a delta next to it. Those pictures just showed you are from the orbit. Those pictures are taken by orbiters, satellite. But on Mars, we have a geologist, which I have multiple geologists who can take pictures and do study right on the surface. And those geologists are rovers. They carry cameras. They carry all the instruments. They can do analysis. They have an arm. They can manipulate some of the rocks. So this picture are taken by Curiosity rovers at Geocrater. You can see this picture showing you the lake deposit, because when there's used to be a lake, those sand, those sediments will start to deposit on the lake bed, and with time you form those sedimentary strata. So there's another evidence there used to be water on the surface, liquid water on surface Mars, although they're dried, as you can tell now. And more different type of evidence, also morphological evidence for flowing water on Mars. This is the conglomerates, fluvial conglomerate, which are the big pebbles carried by rivers, and those pebbles will bump into each other. The rocks will become more rounded than have sharp edges. So the picture on the left are those fluvial conglomerate taken by Curiosity rovers, and on the right is a similar environment on Earth. So you can barely tell them apart. Those pebbles were both formed by the transportation of rivers and things bumping into each other, rounded the rock. As you can tell, that's another evidence there has to be a very strong current. Rivers carry a lot of water, carry a lot of sediments, big rocks they used to be on Mars. Again, if you look at other type of evidence for past liquid water on Mars, we can also find a lot of aqueous minerals. And this histogram just showing you occurrence, the exposure of different aqueous minerals. You don't have to know different type of minerals, but you just need to know those minerals. They either formed in an aqueous environment, or the mineral itself contains water in their formulas. So the discovery of those aqueous minerals are telling us there has to be an aqueous water-rich environment in the past. The water are gone, but those minerals were preserved. And the rover also found a lot of other type of evidence. For example, on the left, you see those white powders. Those white powders right underneath the sand, the reddish Mars sand, the oxidized Mars sand, the hydrated iron sulfates. And those hydrated iron sulfate has to be formed in a water environment. On the right, there are silica. They're hydrated silica, so they also can only be formed in a water environment. And the picture on the left is blueberries, spherical hematite. Those hematite also have to be formed in a water-rich environment. On the right, those are mud cracks. Those are used to be a lake bed, the bottom of the lake, but after the water evaporated, they dried. Now you see all this cracks. So again, all these are scientific evidence showing you there has to be waters on Mars. And if you look at, I showed you different type of evidence. The blue one, this is a map of Mars, and the blue one are showing you the valley networks. All these linear features look like a river, dried river. And the yellow dots are those aqueous minerals. As you can see, they overlap very well. Where you find those linear features look like a dried river, you also found all those aqueous minerals. So that makes sense that they confirmed our discovery using different type of evidence. There has to be rivers on Mars. So with all this evidence, we pieced together a Mars history. Right now, the current Mars is very dry. That's what we know. But in the past, there's still a lot of evidence showing in the past, probably 3.8 billion years ago, the early Mars must be warmer and wet, and there used to be liquid water on Mars, and now it's gone. It's not on the surface anymore. It's not liquid anymore. The reason of that, the consensus among scientists is this: for a planet like our Earth, we have a magnetic field. Those magnetic field will form a shield to prevent the solar wind directly colliding with the Earth atmosphere. So the Earth magnetic field protected Earth atmosphere. That's the case for Mars. Mars used to have a very strong magnetic field, we assume, and those Martian magnetic field form the shield to protect the Martian atmosphere at the early Mars. So the solar wind cannot directly interact with the atmosphere to strip the atmosphere away. But with time, the Martian magnetic field started to decrease. The strength started to decrease. That's determined by the size of the liquid core of Mars. That's related to the Mars core. If Mars core starts to crystallize, you will lose the liquid core, and you need a liquid core in order to generate the magnetic field. So with time, Mars cools down, the liquid core starts to cool down. There are a lot of theories why Mars lost its magnetic field, but we knew it used to have a stronger magnetic field. Now it doesn't have a strong magnetic field. So without the strong magnetic field, solar wind can directly collide with the atmosphere molecules. Those molecules will pick up the energies from solar wind, and they escape away. They get stripped away. This is called solar wind stripping event, the stripping mechanism for Martian atmosphere. With time, the Martian atmosphere become thinner and thinner because there are a lot of molecules has been escaped away through this stripping events. The result of that caused the liquid water on Mars disappeared. It is actually two separate effects. First of all, when you start to remove, first of all, let me explain this figure. This figure is a phase diagram for water. This phase diagram on the x-axis is the temperature. The y-axis is the pressure. So the water, we know the water can be ice, can be liquid, can be water vapor, depending on the temperature. It also depends on the pressure. So on the pressure of Earth, the pressure of Earth is 1 atm, 1 atmosphere, and the blue bar showing the pressure of Earth. The pressure, the phases of water depending on the pressure as well as temperature. So at certain temperature, certain pressure, the water is liquid. At lower pressure, lower temperature, the water is ice phase. And if you increase temperature, you will vaporize water into vapor. So the removal of Martian atmosphere caused two effects. First of all, the Martian atmosphere pressure is low because the molecules is less. There's less molecules, there's less pressure. So, the water, the phase that the Martian condition now is below the triple point of water. The triple point of water means the water could be either water ice or liquid water or water vapor. When you are below the triple point of water, you can, when you change the temperature, you only transform water from ice to vapor. You escape this liquid water phase. So unlike the Earth pressure is 1. So in lower temperature is ice, higher temperature is liquid water, higher temperature is vapor. But because Mars is sitting in an atmosphere much lower pressure, so Mars, even you changing the temperature, you're only converting from ice to vapor. You have very little possibilities to be in the liquid water phase because the pressure has been lower. That's effect number 1. The effect number 2, due to the stripping of atmosphere, is because there are less greenhouse effect. We now know greenhouse effect on Earth. On Mars, there are also greenhouse effect because the atmosphere of Mars is CO2 gas. The atmosphere become thinner, there's weaker greenhouse effect. So overall, the temperature of Mars is also cooler. So that will further push the condition of water into a region. Most of the water on Mars has to be in ice phase rather than liquid phase. So that's what I'm trying to explain. The stripping of atmosphere of Mars causing two effects, lowering the pressure, lowering the temperature. Both of them will contributing why liquid water disappeared on the surface of Mars, because now majority of water on Mars is in ice. So that explains the climate change on Mars from a whiter, warmer surface to a colder, drier surface. The majority of the water, they're probably now in an ice phase rather than liquid phase. Some of the water could also be lost with the atmosphere, because some of the water is in vapor phase, they will be lost with the atmosphere too. But majority of the reason why liquid water doesn't exist is because now they're ice phase. They're either ice in the polar region or they're ice beneath the surface. So that's why we don't find liquid water on Mars anymore. So as you can tell, whether we have water on Mars or not is actually a complicated problem. You could have two separate parameters controlling whether you have liquid water on Mars or not. The first controlling factor is temperature. As you can see, the horizontal line, the surface temperature, if the temperature is low, you have a cold environment, the water will store in the ice sheet. If you are a warmer environment, you are promoting more water become liquid. On the y-axis is another independent parameters controlling how much liquid water on Mars, which is the initial water budget on Mars. This is actually my study is mostly focusing on. We're focusing on quantify how much water did Mars actually have. But that's why I want to explain there is complicated problem. Sometimes people think about the water is gone because of temperature change, but also an independent controlling factor is the initial water budget. If the initial water budget is high, you have higher possibilities to have liquid water. So just to show you some schematic figures, the x-axis are time. 4.5 billion years ago is the starting point of the Earth and the Mars, the starting point of the solar system. The y and to the right is now current. The y-axis is liquid water on Mars. As you can see now, I have no scales. This is a schematic figure, so I have no scale. Mars has very little water now, and we know Earth has much more water than Mars. And then if you compare early Mars with the current Mars, we know early Mars must have a lot of water. The problem and the reason why the current Mars has less water is because a lot of liquid water on Mars in the past now stored as ice in the polar region or underneath the surface, or some of them has been lost to space. But the problem is, did early Mars ever had as much water than early Mars had ever as much water than Earth, or less? We don't know. We know qualitatively early Mars has more water than Mars now, but we can't compare early Mars with Earth. All this evidence I showed you early on, none of them can give us a quantified number. We just know, oh, there used to be water. Must be. There's so much evidence showing you there has to be water, but how much in total? Some people imagine, oh, early Mars could be as wet as our Earth. But my conclusion from today's talk, I'll show you later, is actually early Mars has never had as much water as our Earth. So my question to lead to my own research is, we knew early Mars has water, but how much? How do you compare with Earth? Was Mars ever as wet as our Earth? Could you have like an ocean, like oceans of water on Mars, or just a little bit of water, like with lakes and rivers? So that's the question I'm trying to answer. You can't use remote sensing. You can't use rover studies to give you a total, to calculate a total number of water on Mars, because the remote sensing, you're only looking at the surface of Mars. The rover studies, you only study one point, one location on Mars. And you wouldn't infer there could be a lot of water, but you just can't quantify. In order to quantify how much water had early Mars ever had, we have to study Martian meteorite. So here I'm just quoting someone. Where did water come from? Martian meteorite can tell stories of Mars water history. And the picture on the left just showing you one of the famous Martian meteorite, Black Beauty, NWA in 1734. But there's more than 100 Martian meteorites. So before I move on to my own research, I just want to give you a little bit introduction about Martian meteorite. Martian meteorite is also called SNC meteorite because SNC, as you can see, those three meteorite was first discovered, like the Shagoti, Nahla, Chassidni. So those meteorite was first found on Earth. And so that's why those type of meteorite, Martian meteorite, was called SNCs. And they're made with different kind of mineralogy. So they're different type of rocks. Different Martian meteorite, they're not the same. They're not the same mineralogy and petrology. They're like our Earth, has a diverse type of geology on Mars. So you can imagine Martian meteorite representing different mineralogy. In total, the last time I checked, there's already 159 Martian meteorite has been identified on Earth. So those Martian meteorite can help us to quantify how much water on Mars. Just in case people are interested, how do we know Martian meteorite are from Mars? And this figure on the right is the killer evidence why we know Martian meteorite are from Mars. This figure showing you the composition of different different gas compositions measured in the bubbles trapped in Martian meteorite. Those Martian meteorite used to be lavas. There used to be rocks on Mars. When they formed or when they were ejected by impact, those rocks will be melted. When you melt those rocks, you can trap some atmosphere composition in the bubbles. So after the meteorite fall on Earth, if you cut the meteorite, you can release the gas from these bubbles. And those gas compositions are representing Martian atmosphere composition. So, and the y-axis of this figure are showing you Martian atmosphere composition measured by Viking landers. So those landers, when they land on Mars, they could measure what is the current atmosphere composition of Mars. So it matches very well with the Martian meteorite. So that means those meteorites are from Mars, and those compositions are very different from Earth atmosphere. So that give us the indication those meteorites are from Mars. A Martian meteorite has a variety of age. The x-axis showing you the crystallization age of those meteorites. The y-axis showing you how many samples in that age. As you can tell, the meteorite could be 4,000 million years. 4,000 million years means 4 billion years. There are also meteorites younger, like 150 million years. But those Martian meteorites we study covers a huge range, covers several billion years. So this gives us an idea. We can study the Martian composition over the time. And this is just showing you the composition of Martian samples. You don't have, if you're not a geologist, you probably don't have to pay attention to this. The x-axis is silicon number, the y-axis the sodium potassium number. This is how geologists used to classify rocks on Earth. So we can also classify rocks on Mars using this. From orbit, those orbiters can measure the surface composition. The surface composition of Mars plot in this basalt range, this the blue range. If those rovers, the rovers carries all these probes on rovers, and they are walking around on surface of Mars. They actually found more diversity of type of rocks on Mars. But if you look at Martian meteorite, they're actually representing a very different composition. You don't have to know the details about this figure, but you just need to know the chemical composition of Martian meteorite are different from the composition you measured with rovers or the orbiters. Because the orbiter, you only measure the surface compositions. You are reading a book from the cover. The in situ measurement by rovers, they're only measuring those rocks exposed on the surface. But Martian meteorite, assuming coming from deeper region of Mars, they're representing the bulk composition of Mars because some of them even from the mantle much deeper than the surface. So those Martian meteorites can give us overall evaluation of the volatiles on Mars. So how do we really evaluate the volatile composition on Mars? And this is another figure showing the elemental composition. Let me explain to you in details. We're going to look at this figure multiple times. The x-axis showing you the different elements. The elements are not randomly ordered. The elements are ordered in a way, the most refractory elements on the left, the most volatile element on the right. So those elements on the left are very difficult to be volatile, to be volatilized. The elements on the right are very easy to be volatilized. The y-axis are showing you the composition compared to CI chondrite, CI combination chondrite, because CI combination chondrite representing the bulk solar system composition. That's the starting point of our solar system. So the blue point are plotting the measurement of Earth rocks. The Martian samples are plotted in red. So you see there's a progressive depletion of elements. I'm just showing you the trend. The Earth, both Earth and Mars, for the elements, if the elements are more volatile, you would get depleted more compared to the solar composition. If the elements are very refractory, you get the same value as the bulk solar composition, the CI chondrite. So this trend, this progressive depletion trend versus volatility is telling us during the formation of planets, they're losing volatiles. So different planets were losing different amount of volatiles, and for the elements more volatile, you lose more. For the elements in not volatile, it's hard to lose. So that's the trend showing you. In this plot, I only plotted moderately volatile elements. I didn't plot highly volatile elements. As you know, highly volatile elements like water, they're very volatile. They're easy to be gone. Their concentration are very, very low. So it's very hard to directly measure water. So we actually measure a lot of other elements using this trend to extrapolate what could be water and other highly volatile elements to be when you compare Earth and Mars. Because if you directly measure water, it's just so volatile, it's hard to measure. It's hard to measure precisely. But if you measure many other elements, they will form a trend, the trend giving you the extrapolation, what the water could be in the end. So as you can tell, Mars and Earth, they fall on the same trend, which means the degree of volatile depletion of Mars and Earth are the same. If Mars or Earth depleted more volatiles than the other, you will see a higher slope. You'll see more loss for the same element. So back to 1980s, and those measurements were done by using meteorite. That's how we can evaluate the bulk Mars composition, because you can't evaluate the bulk Mars composition using rovers, using remote sensing, because you don't get the interior of Mars. We can only get the interior of Mars composition using meteorite. So back to the 1980s, people proposed Mars is a volatile rich planet. And people really like this conclusion because this conclusion is agreeing with all this surface topography, surface morphology evidence. It used to be waters. They didn't know how much water, but now the meteorite study telling us, oh, the Mars is as volatile as Earth. And last year during COVID, someone even published another paper. They did more measurement, more precise measurement of the same Martian meteorite, and they also compared to Earth. The trend of Earth and Mars, they're separated. The Mars has a smaller slope, which means less depleted in volatiles, which extrapolating the water of Mars has to be higher. The initial amount of water on Mars, the bulk amount of water on Mars has to be higher than Earth. So they say, oh, Mars is even more volatile rich than Earth. So that will give us a really interesting idea. The early Mars has to be, if the temperature is right, the temperature is good enough, there should be a lot of water. There are probably oceans of oceans. Now, our current Earth is covered with 70% of oceans. Imagine how much percentage of surface of Mars will be covered by water if there are even more initial amount of water on Mars. So do we really assume the early Mars is like this imaginary picture drawing by people as wet as Earth, but today's Mars is like this? How could we got from that to this? Or maybe the previous study was wrong. Maybe the previous study, the implication was not exactly correct. Maybe there's other interpretation. So that's lead to my recent study. So if you look at this slope, you don't have to get this slope by measuring all the elements. You just need to measure one volatile element, one refractory element very well. This ratio will give you the slope. So if this ratio is high, that means the volatile of Mars is high. If the ratio is low, that means the water budget of Mars is low. So this ratio, we can pick two elements, which is potassium and thorium, because potassium is very volatile, thorium is very refractory. This ratio, potassium-thorium ratio, is a tracer of volatiles for interplanetary comparison. As I said, potassium is volatile, thorium is refractory. Both are lithophile elements, so their ratio do not affected by other processes. And also, both potassium and thorium are radioactive. So because they're radioactive, they can detect it remotely by remote sensors. So they can be widely available for many planets, including Mercury and Venus, because we do not have a lander. We do not have a lander on Mercury and Venus. How do we study the volatile budget of Mercury and Venus? But we can use this ratio. If you look at this potassium-thorium ratio across the solar system, the x-axis giving you the heliocentric distance, the y-axis give you the potassium-thorium ratio of Mercury, Venus, Earth, and Mars. As you can tell, the error bar of this measurement potassium-thorium is really high. You can't really distinguish all these four planets, Mercury, Venus, Earth, Mars, they're about the same range. It's hard to really quantify to say which one's higher, which one's lower. We'll have a smaller error bar, of course, for Earth because we can do much precise measurement for Earth. So using potassium-thorium ratio only give you a rough idea how much volatile elements the planet has, but you can't really compare different planets in details. And this is a more detailed figure. I'm just going to ignore it. This is just showing you, if you measure different Martian rocks, you get a very wide range. And it's hard to really tell what is the average value for the total Mars entirely. So it's very difficult. So come to my study, and the paper we published like last month in September is actually proposing a new tracer of volatiles for interplanetary comparison. This new tracer is called potassium isotope. It's using two isotopes of potassium, potassium 41 or potassium 39, using this ratio to indicate the volatile loss. If this ratio is high, which means the planet has lower volatiles overall, including water. If this ratio is low, means this planet has more volatiles. The idea, the logic of this is potassium 39 is in the denominator. Potassium 39 is very light compared to potassium 41. It's lighter than potassium 41. So when you have volatilization, the lighter potassium will be gone, will be depleted easily, easier than potassium 41. So you increase this ratio. The more volatile loss you have, the ratio will go higher. So what we did, we actually measured samples from 4 planets, samples from Earth, samples from Mars, samples from Moon, and samples from Vesta asteroid. And interestingly, we see the x-axis is the ratio. We found the isotopic ratio of Vesta is higher than the ratio of Moon, is higher than the ratio of Mars, and higher than the ratio of Earth, which indicating Vesta is drier than the Moon is drier than Mars, and Mars is drier than Earth. And this is just including our data. You see the blue one is lower, Mars is slightly higher, Moon is even higher, Vesta is even higher. And if you plotting this new tracer, potassium isotope, versus a planetary size indicator, such as radius, mass, surface gravity, escape velocity, all of those parameters are linked with the size of the planet. You see a very good correlation between potassium isotope and those size parameters, which is suggesting, which is telling us that this is probably not random. There's some mechanism behind it. And if you also compare this new tracer potassium isotope with another tracer, which is manganese over sodium ratio, manganese over sodium ratio is another indicator of volatile depletion proposed by other people in the past. Sodium is more volatile than manganese. So when you lose volatiles, this ratio will become larger because you're making sodium smaller, manganese over sodium ratio larger. So you see our new tracer potassium isotope agrees with the manganese sodium old tracers. They correlate very well. The planet like Vesta, they're very dry. They lost a lot of volatiles. They have a higher potassium over potassium ratio as well as a manganese sodium ratio. Similar, if you look at Mars and Earth, Mars has a higher potassium over potassium isotopes as well as manganese over sodium ratio, which indicate two tracers are telling us Mars are more volatile depleted than our Earth. So if you ask me what actually caused the loss of volatiles and loss of water, it's because when those planets formed in the beginning, there were a lot of impact. Those impact will generate melting, vaporization, and some of the vapor will be lost. And how much vapor will be lost is related to the size of the planet. The smaller the planet, the smaller the escape velocity, so the vapor can be easily lost. The larger the body, the more difficult for the vapor to be lost. That's why our Earth remained a lot of volatiles, because our Earth has a larger size. Here again, you don't have to look at the details, but the point of this figure showing you the escape velocities of larger bodies are mostly too high to be exceeded by silicate vapor molecules, which means the smaller the body, the more easy to lose volatiles in the beginning. Between Mars and the Earth, Mars just never had enough volatile to start with because Mars is much smaller than our Earth. This conclusion is based on from our relationship between the potassium isotope with the size parameters. Okay, one more link between potassium isotope and water. In the past, in the past few minutes, I have been linking potassium with volatiles, but can we really link potassium with water? There are another tracers of water in the past has been proposed, which is a hydrogen isotope. Hydrogen isotope is a traditional tracer of water for interplanetary comparison. People have been studying hydrogen isotope. Hydrogen is an indicator of water. So they have been studying hydrogen isotope and then using that to back calculate what is the value for bulk water budget for different planets. As you can tell, those measurements, those calculated value for bulk water abundant on Earth, Mars, Moon, and Vesta agree with our potassium isotope. Our potassium isotope shows the lower value, the lower potassium isotope, you have a higher water. So two separate indicators pointing to the same thing. Mars has less water than Earth. So we even propose potassium isotope is better tracer than water itself, because water is very volatile. They transport it all the time. So if you look at our Earth, some places are very dry, some places are very wet, because water is very active, very mobile. So they move around. Potassium is volatile, but not as volatile as water. So it's more a conservative tracer for water itself. It remains in the information from the beginning of the planet formation. It doesn't get moved around like water. So it's an easier tracer to use than water itself. So to conclude, decades of orbital in situ observations exhibit evidence of a wet early Mars where liquid water on the surface were indeed present, however limited and only episodically available. And elemental models based on Martian meteorites suggested a more volatile-rich bulk Mars than Earth, which is not consistent with orbital and in situ observations. And the new potassium isotope traces found Mars has a more fractionated potassium isotope than Earth, which indicates early Mars accreted less or lost more volatiles than Earth. And then we extrapolate from volatile elements to water, and because water is one of the highly volatile species, and early Mars accreted less or lost more water than Earth. And we also found this correlation between potassium isotope and mass is also observed between Earth, Moon, Mars, and Vesta, hinting that there's a ubiquitous mechanism for loss of volatiles of solar system. So to conclude, we through our study, we think early Mars has never as enough water as our Earth, although there used to be water, liquid water on Mars because the climate was different, but you cannot expect as much water on Mars compared to our Earth. And this study, our study also have implications to exoplanet, because right now, astronomy, there's so much interest looking for planets orbiting other stars. We can't study those planets very well because they're so far away. But how do we know whether they have water or not? One determining factor is the size, because through a case study of our solar system, at least the inner solar system, the water budget of the planet is related to the size of the planet. So when we study other planets, exoplanet, we can use the size as some kind of screening factors to determine whether those planets has water or not. And then further move from water, we can probably assume whether those planets are habitable or not. Okay, thank you very much. I would like to thank all my collaborators who have contributed in these studies, and I would like to answer your questions if you have any. Thank you.
Well, thank you very much, Kun, and hopefully everyone can show with reactions or appreciation. We do have a couple of questions in the chat, and so let me get to those, and then we will invite folks to just unmute themselves and ask questions as they wish. Here's one. You showed a phase diagram of liquid of water showing the stability fields of ice, liquid water, and water vapor. What happens if there's dissolved salt in the water? How does that affect that triple point?
Yeah, that's a very good question. I didn't mention that. You can't, that's the phase diagram for pure water. If you have salt dissolved in water, you shift those boundaries. Yes, you can't have pure liquid water on Mars right now because the pressure is too low, the temperature is too low. But if you have salty water, brine, they could be liquid, they could exist on Mars. But you can't have, that phase diagram only showing you the pure water. If you add salt in, you shift the boundaries between different phases. Then you could have salty water on Mars, even right now.
Right. Yeah. In fact, it shifts a little bit to lower temperature and lower pressure, right? So yeah, that's very consistent with what you're saying. Here's another question. You showed, you talked a little bit about the mineralogy that has been sensed by the rovers and from orbit. And I think one of those showed carbonate minerals, although not very abundant, there are carbonate minerals. How do they form on Mars in a low oxygen environment is the question.
Oh, let me get to that figure.
Oh, I don't know that you have to go all the way back to it. It's just where they're, the observation that there are carbonates.
Yeah, I am aware there's carbonate found on Mars, but I don't know the exact chemistry forming carbonate on Mars. It is a good question because on Earth, a lot of carbonate were formed related by bioactivity. So I think you are trying to infer, saying if you found carbonate, is that like a sign of kind of life, kind of some bioactivity on Mars? I don't know, but I think I listened to some talks in the past, some more experts studying the formation of carbonate. There is a abiotic path to form carbonate on Mars.
Well, the other question is, I mean, the other issue would be what is meant by a low oxygen environment. I mean, after all, oxygen is still the most abundant element at the surface.
In the rock, yes.
So, yeah, in the rocks.
In the rock,
so,
oxygen is very abundant.
Yeah, yeah. And so even though it's not present maybe as free oxygen, it's there as CO2 or carbon monoxide.
Yeah, CO2, yeah, exactly. CO2 is so abundant. You just precipitate.
Yeah. There was a question from Jake Miller, and maybe Jake, you would want to ask this question because I'm not sure exactly which figure you were asking about the order of the elements on the x-axis, and I think it might have been a volatility figure, Kun, where you showed volatility of the elements.
Yeah, I think it's this one, I guess.
Jake, feel free to unmute yourself if you want to follow up that question. Or maybe you could just, I mean, you can just talk about this. I mean, clearly they're listed in order of volatility, but you might say what that volatility is based on.
Oh, okay, yes. Those elements are not the typical order of element you see from periodic table. The periodic table is showing you the elements according to their proton number and the photon number, the atomic structure. But this volatility is based on their thermodynamic properties. Those sequence of volatilities calculated using thermodynamic calculations based on the thermodynamic properties, and particular those elements, the sequence of those volatilities are actually calculated by a professor at WashU, Katharina Laudes. So you should ask her how did she calculate this order of the elements. And she's the world expert, everyone using her order of volatility. But different people do calculate the volatility differently, slightly, because they're using different experimental data from thermodynamics. Some people using some kind of different equations. So this range of volatile depletion trend is slightly varies depending on which volatility you are using. But they're not based on atomic number, not a proton number, neutron number structure of the atoms. It's based on their thermodynamic properties through experiments.
Kun, here's another one. This is a tough one from Ken Coppersmith. How much water is estimated to be below the surface of Mars?
Oh, I don't know the number, but I know you're talking about there are some people that are trying to do modeling to see how much water could be stored as ice underneath, but I don't see a really reliable number because there's no directly way to measure it, and people just using a different assumption. So I can't answer you how much in terms of a number. We just know there is, based on rover studies, there has been some ice being found underneath, but I don't know how much globally you can estimate based on some point estimate.
Yeah, I know our colleague Than Putzig, who has worked with orbital data and radar data in particular, has used radar to make some estimates in the subsurface, and some of that can pretty deep. And so it's very interesting work being done in that area, but it remains, I think, a very difficult question to answer.
Yeah, there's water either in the polar region under the ice cap. There could be also globally distributed just underneath the surface, buried by the sand.
Yeah. Okay. Here's another good one. Going back, and you've got the right plot up, the volatility plot. The question is, the comment is, I have a hard time accepting that fluorine is less volatile than copper or nickel. Do you want to address that?
Oh, okay. Okay, you're right, because those volatilities are depending on the condition. This volatility also depending on their speciation. This trend, this sequence I'm showing you is calculated at solar system initial condition, which has a very different temperature and pressure. And the speciation for those elements, they don't form the normal species we see on Earth in a higher pressure environment. And also, it related to availability of elements. And those calculations were done using solar hydrogen-rich environment. That's also different from the Earth environment. Yes, the volatility also depending on the pressure, temperature, also depending on the speciation. If you calculate this at different environment, different condition, you get a different number, different ranks.
Okay, here's Liliana has a couple of questions. Liliana, would you like to unmute and ask them yourself, or would you prefer that I ask them?
Yeah, I can ask them. But earlier on, some years ago, there was I think Scientific American or somewhere that theory on how the atmosphere was lost by a broken dynamo in the core. I mean, dynamo effect in the core of Mars, maybe due to impacts and so on. Is that still the prevalent theory? And the science fiction question is, could we change anything in the future if we are going to plan to go to Mars? And do you want to still lose atmosphere?
Yeah. I see. I saw some news in the last few years. They were trying to put some device right in front of Mars, between Mars and the sun, and they're generating an artificial shield to prevent the solar, to have a magnetic field in front of Mars before the sun, so to protect the solar wind to colliding with future atmosphere, so the atmosphere will eventually build up. So I don't think engineering wise that's possible. There are a lot of the scientific wise is possible, theoretically is possible, but it's engineering very costly. But those solar wind stripping, changing the atmosphere, they're very slow. So for human time, I don't know how much atmosphere you can build. Even you can stop the solar wind interaction with current Martian atmosphere now. It's just beyond human lifespan. All this thing you can do. You have to do extreme thing, not the natural process, in order to build up the Martian atmosphere. Yeah, but I do see people trying to put a magnetic shield in front of Mars, a concept idea, trying to create an artificial magnetic field for Mars for the future, and eventually we'll get a habitable Mars again. It's theoretically it's possible. Just not. I don't think we can see it anytime soon.
Good one for future engineers.
Yeah, that's like science fiction, like hundreds of years from now.
It is still thought that it's the internal dynamo is broken. I mean, they show some remnant magnetism that is only on one side of the planet, not in the rest, that kind of thing. I don't know.
Yeah, I think we don't really know why the Martian magnetic field lost. It's related to the core. Because the magnetic field is generated the motions of the movement of the liquid core of Mars. Some people say the liquid core get squeezed, become crystallized. The other ideas. So I don't really know why we lost the Martian magnetic field to start with. So we don't think we can get a really solution how to reverse that process.
We are not going to go to the core.
We don't even know the Earth.
That's even more difficult.
We heard in a colloquium yesterday that the seismic data, new seismic data from the InSight mission is indicating that the Martian core has light element components, and it's less dense than perhaps well, Quinn, you may have heard the talk and have more up-to-date information.
Yeah, I thought they were saying the Mars core is larger than what we thought. So I don't remember. They also have a light element, but I don't know. I don't think I remember too well what they.
Yeah. Well, it's curious.
Mm.
It's curious because, you know, the moon still has, we think according to the best measurements of the wobble of the moon, that it still has a liquid inner core, I mean, a liquid outer core and a solid inner core. And so it's still crystallizing. But of course, the moon no longer has a magnetic field. And so it's moving such that it doesn't generate a dynamo.
Yeah.
And maybe this is the same case with Mars. So let's see, other questions. While others are queuing up their questions, I guess I have one for you. And it has to do with, you talk about the volatilization effects of giant impacts, which mainly occurred early in planet's history, moon and Earth and Mars and so forth. And also of, you know, big magmatic activity events that cause degassing. The question is on Earth, I wonder if we could say anything about when those events might have taken place, if we could study the potassium isotopes in very, very old rocks. I don't know that they're any old enough because, you know, we have to have potassium in them and they have to be older than 4-point-something billion years.
Yeah, I understand your question, Brad. The volatility, potassium is not super volatile. So during volcanic eruption, we don't see, in the vapor, we don't have potassium in the vapor. It's not that volatile. That's why potassium is very conservative tracer. It doesn't change much since the beginning. You only need like a relatively violent events in the early history during the planet formation. You can fractionate it, you can lose the vapor. And then after that, the volcanic degassing from a volcano doesn't really change potassium isotope. That's the good thing about potassium, but not good for your purpose. We can't, we indeed measured a lot of volcanic rock. We measured a lot of Iceland rock. We don't see any fractionation for potassium. It didn't lose, potassium didn't get lost into the vapor during the volcanic degassing because the volatility is not that high. So, we can't use it to trace the initial volcanic events on Earth. Some other element maybe, but those elements, very volatile, can be lost in volcanic degassing. They get lost everywhere, every process. So you get overlapped with all these different events. So it's hard to tell.
So here's another question. And I don't know if this is one that you have the answer to, but what's the current status of ammonia and methane on the surface of Mars?
Oh, I don't know the number, but I know some scientists, they study, they keep tracking that, but I don't know the new measurement. This is a good,
this may be a good segue into a quick advertisement about next Saturday's talk, when Scott Van Bommel will be speaking again about Mars. And Scott is associated with the Perseverance mission. He's been associated with all of the rover missions since the MER, the Mars exploration rovers. And he may very well have, you know, be right up to date because he's right there with all the rover team meeting when they're talking about these measurements. So yeah, and I confess that I don't have the latest and greatest info either.
Yeah, definitely come to Scott's talk next week. Scott is a rover person. He just every week they have update from rover all the time. They control the rover, so he knows more about rover. And my study mostly focused on the meteorite, and the meteorite gave us a bulk view, overall view of the Earth, of Mars, particularly in the past, because most Martian meteorites are very, very old.
Yeah, that view behind me, that's Mars, and that was taken with one of the Mars exploration rovers. It's a little, my interpretation, that's a little volcanic vent, and so would have been part of a process that was causing some degassing on Mars way long ago. Any other questions? Oh, here's one. in 2017, Jim Green, who was at the time the what was Jim? He was the head of the Planetary Science Division, I think. Either that or he had just become the chief scientist. Proposed a 1 to 2 Tesla magnet located at Mars L1 would be enough to create an atmosphere. There are a lot of ifs and even more engineering and financial questions, as stated. Yeah, that's a good one. Anthony, I don't know if you want to follow that up at all.
That is the news I saw last time. That's the news I just mentioned. That's what I saw last time, like years ago when I was teaching the solar system class. I think I mentioned that to my class. That's the one I was thinking. But time-wise, I mean, there's so many issues with it, but I don't know how fast you can build up the Martian atmosphere through the volcanic degassing, the natural events. It's just not possible for human span, like a geological time. Geological time, right. And the other thing I would say is I know Jim Green, and he's a tremendous optimist. Very optimistic. It's a very good idea, a very good concept. Okay, I guess last call for questions. Any last thoughts? I'm trying to monitor for raised hands. I don't see any, but again, if you want to just unmute and ask your final question. And if not, we'll say going once, going twice, and then 3 times. Thank you so much, Kun, for a very interesting and enlightening talk. And good luck with your research going forward. Very interesting stuff you can do with isotopes. Thank you all for attending. It's been great to have you, and hopefully we'll see many of you back here on this channel next Saturday. And go and have a great weekend. It's a beautiful day if you happen to be in St. Louis. The colors are spectacular. So take care, everybody. Thank you, Kun. Thank you. Thank you, everybody. Thank you.